Welcome to The Explainer. Today, we're diving into something pretty wild, a breakthrough that reveals a hidden, and I mean deeply hidden, connection between the AI that powers language models and the fundamental physics of how memory works. All right, let's just jump right into it. What on earth could AI language models and the physics of memory possibly have in common? I mean, on the surface, they feel like they're from completely different planets. One writes poetry and code, the other helps explain how our own brains work. But as it turns out, they might just be two sides of the very same coin.
So, to really get this, we got to meet our two main characters. These are two incredibly powerful ideas in AI that, for the longest time, have pretty much lived in separate universes.
Okay, so in one corner, you've got the heavyweights, Transformers. This is the tech behind pretty much everything you hear about in AI. GPT, BERT, you name it. They are absolute masters at understanding the context of language. Then, in the other corner, you have these things called Hopfield networks. Now, these are a classic idea from the 80s, inspired by physics to mimic how our brains do associative memory. You know, like when you see just a little piece of something and your brain instantly fills in the rest.
And this timeline, man, it just lays it all out, right? Hopfield networks pop up way back in '82, they get this major upgrade in 2016, and then just 1 year later, in a totally different part of the AI world, boom, Transformers crash the party and change the game forever. For years, they were on completely separate tracks. Until now, a new paper finally built the bridge.
Okay, so this is where it gets really, really interesting. How do you build a bridge between these two worlds? Well, the secret sauce, the hidden connection, comes straight out of a physics textbook.
And that concept is called an energy landscape. Okay, picture this. You've got a bunch of hills and valleys. If you drop a ball, what's it going to do? It's going to roll downhill, right? And it'll eventually settle in the deepest part of a valley. That low point, that's its lowest energy state. It's stable. In Hopfield networks, those valleys are literally the stored memories. The whole network settles into the memory it's trying to remember.
Okay, now let's switch gears and you get the transformer. This right here is the famous attention formula. It looks, well, like a math equation, right? It feels very direct. You plug in some numbers, you do the calculation, and boom, you get an answer about what the AI should pay attention to. A one-and-done deal. But then, this new research comes along and proposes this energy function. And you can see it looks totally different from the attention formula. It's describing a whole landscape. And this is where the magic happens. Get this. The big reveal is that if you find the absolute lowest point in this new energy landscape, you know, that stable valley where our imaginary ball would stop rolling, the spot you land on is exactly the same as the answer you get from the original attention formula. So what we all thought was just a direct calculation is actually a search for the most stable state. It's a physical process. Okay, so that's a really cool connection for sure, but it's way more than just a neat academic trick. Because if attention is just a system finding its minimum energy, well, that opens up some wild new possibilities for making it way, way more powerful.
And here's the big question it raises. What if the map of that energy landscape could be more interesting? You see, standard attention is like rolling a ball into a single, perfectly smooth bowl. There's only one place it can end up. But what if we could design landscapes with winding canyons, multiple valleys, and complex terrain for the model to navigate? This is a great way to think about it. Using simple, linear attention on complex data is like trying to draw a straight line through a bunch of points that form a curvy wave. It's just never going to capture the real pattern. But a nonlinear model, that's like having a flexible ruler that can bend and weave to trace that complex shape perfectly. And that's precisely what this new framework gives us, nonlinear attention. We can now tweak that energy function, make it more complex, quadratic, exponential, you name it, and create that much richer landscape. And that means the model can start to pick up on way more subtle, sophisticated patterns in the data that a simple model would just completely fly past. Okay, so why should you care? Why go through all this trouble? What are the real-world practical benefits of making our AI models explore these more complicated landscapes? Well, the potential payoff here is massive. We're talking about models that could finally get sarcasm or understand really tricky metaphors. They could become tougher, more robust, so they don't get thrown off by a simple typo. And here's a wild thought. A more complex landscape could actually make the training process smoother and more stable, which is a huge deal for these enormous models. And the best part?
This isn't just some high-in-the-sky theory. The folks behind this paper actually laid out a step-by-step algorithm for how to build these new, souped-up downlinear attention mechanisms.
So instead of that one-and-done calculation, it becomes a process. The model starts with a standard answer, but then it gets to, well, roll down the hill of this new nonlinear landscape. It takes a few steps, refining its focus each time, until it settles into an even better, more stable spot.
And this table really breaks it down for us. The old way, the linear way, is a direct shot. It's simple, it's fast. The new, non-linear approach, though, that requires a search. It takes more computational horsepower, no doubt about it. But in exchange for that cost, you're letting the model explore a vastly richer world of possible answers. It's the classic trade-off, speed versus sophistication.
So what's the big takeaway from all this? It's pretty profound, actually. This reframes what attention really is. It's not just some clever math trick for processing sentences. It's a form of associative memory retrieval. The AI is literally pulling the most relevant ideas from its memory by finding the most stable energy state. And that brings us full circle, connecting it right back to the original inspiration behind those Hopfield networks from the 80s.
This whole unified view just leaves you with this one massive question. If the attention mechanism at the heart of our most advanced AI is really just following a law of physics, what other fundamental laws of nature are hiding in our code, just waiting to be discovered? It really makes you think about the deep connection between intelligence and the universe itself. Thanks for joining me.